So momentum 6.1. Momentum is P equals mv.
Okay, so what do we call P? Like, is it a momentogram or?
No, it's momentum. P is momentum.
Or are you asking about
Okay, well, what if we say, oh, it's 54, or what? 50?
Well, like
Oh,
m
units?
is mass, so we can't use m for mass. So it's P. P is momentum. And the units are kilograms meters per second. It doesn't have its own special unit.
Yeah, that's something you said something has momentum.
Wait, what are the SI units? Or kilograms?
Kilograms meters per second.
Okay.
Kilograms.
Because it's mass, which is kilograms, and then velocity meters per second. It doesn't have its own special units. Like force is newtons. Momentum doesn't have that.
Wait a second, are we still recording?
Mm-hmm.
Oh, okay. I regret momentum grams now.
I still see a red cup. I mean, I can see the blue cup, but I still see the red cup. Is that your way of hiding it? Okay. Okay, so momentum. You can still break momentum down into two different components, the x component, the y component. So since mass is not a vector, mass is a scalar, it doesn't have an x and y, it's just mass. And you just multiply it by either dx or dy. So you can have like p I hat and p j hat. It happens when I type so fast.
Bless you.
My left hand types faster than my right hand, so I end up with
Oh, that actually explains a lot.
So kinetic energy, we can relate momentum to kinetic energy by doing momentum squared, so p squared over 2m. And this is pretty easy. I have to think about it for a second. If kinetic energy is 1/2 mv squared and p is equal to mv, basically they just rearrange it so that it'll fit in there. So like if you had p squared is m squared v squared, and solve for v squared. There you go. You got it. Equals v squared. You're going to replace this right here. So this will be 1/2 m, and then p squared over m squared, and that'll be 1/2 p squared over m, which simplified looks p squared over 2m. So that's where it comes from.
Wait, but
Okay, I'm glad I didn't.
so p squared equals m squared v squared, right?
Yes.
Shouldn't it be p squared equals 1/4 m squared v squared?
No. This is the equation for kinetic energy. This is the equation for momentum.
Oh.
So I was trying to get momentum in there, and I needed a v squared.
Okay.
So they're two separate equations, and I'm putting them together.
All right.
Okay, I see one red cup.
Oh, no, just ignore that.
Okay. So impulse. In order to change the momentum of the object, a force has to be applied, right? This is Newton's second law, or first law of inertia. That an object doing something will continue to do whatever it was doing until an external force is applied to it. So unless you apply a force, that is not going to change. When you do apply a force, now you're going to have a change in velocity, which means a force is going to change your momentum.
Wait, I thought that was the second law. The first law was.
The first law is inertia.
Yeah.
Second law is F equals ma.
Yeah.
And third law is action and reaction.
Reaction. Oh, okay. I thought it was reaction, then inertia.
Oh, nope. So if you take F equals ma, a is the change in velocity over the change in time. Bring time to the other side, and you get ft equals mv. So this ft, this force times time, is going to change your momentum. The longer the force is applied, the more momentum you're going to have, or change in momentum. Yes?
Oh, okay. So does F equal momentum then?
F times t equals
P equals
momentum, right? P is momentum. F times t will equal momentum.
Oh, okay. So, well, I mean, if t equals 1 and F equals P, then.
Yes.
Anytime times 1 is going to be itself.
Oh yeah, what do we call a force? Wait, no.
Force is newtons.
Yeah, okay, yes.
Times second. And
Equals whatever.
momentum is going to be kilograms meters per second, but it could also be Newton seconds.
Newton seconds, okay.
Yes, that is another option for your units.
Okay.
They are equivalent. O'Brien.
Oh.
Thank you. All right, impulse. So this force times time is what we call impulse. We can't use I for impulse because I is moment of inertia. So we use capital J. I know it's a little weird, but it is capital J. And this impulse is the combination of force and time put together to change that momentum. You can think of impulse kind of as impact. Impact is more like force related though, but impulse is the force and the time together. So it's like the time of the impact is one really small. But it's like, usually we deal with impulse when we're talking about one object hitting another and that object isn't moving. So for instance, like if I throw the duck at the wall or throw something against the floor. The floor is a solid, it's going to have that external force.
Okay.
You're really only looking at one object in the case of the interaction between the two.
So impulse is the reaction to the action of the duck hitting the floor.
I mean, it's action as it was thrown and reaction as it bounced back.
Yeah, but the impulse is a reaction, right?
It's kind of the connecting the two. It's connecting action to reaction, if you want. But the force of the duck hitting the ground is the same as the ground when the duck hits. The force is exactly the same.
So that's what it means when for every
Action is an equal and opposite. It means that the duck hits the ground with 5 newtons, and that ground feels 5 newtons in the opposite direction.
I thought it was like, because I never understood. It was like if you throw a ball at a thing, like it's not going to come back the same distance.
No, that's where the momentum is going to come in. It doesn't. That law is not talking about that.
Okay.
It is only talking about like I'm touching the table's touching me. So the force between the two things needs to be exactly the same. It's not talking about like cause and effect, which is what a lot of people think about it.
Okay.
It's not the same. This is what an impulse looks like. Notice that it is not just no force and then force. As the object hits, it slowly gets more and more force on it. That's like you can see the duck is deforming here until it's all the way squished up, and then it starts to deform as it moves away. So the force is like this. So the duck deforms, and then turns around and gets less. So it's less force, more, and then starts to get less and less.
Okay, on the way back though, it reforms, right?
It reforms. Mm-hmm.
Okay.
So you can see that it starts off with a little amount of force and then reaches some sort of maximum force and then goes away. When we do this, we usually talk about force as an average force to make it easier. But if you are looking for the exact number and you're given like a graph like this, you can find force times time, which is impulse, by finding the area under this curve. So that would find the exact. For most of these problems, we're just going to take the average. Look how bored Nick looks.
He's like, I already know all of this in the next 5 chapters afterwards.
All right, so the force, or the equation just for impulse, force times time. Now, all these things are equal to each other. Impulse is equal to force times time, which is equal to the change in momentum, which is equal to mv final minus mv initial. They're all equal to each other. And you can, use the parts that you need. But impulse is basically the force over some sort of time interval. Here's the graph. And you can also use that by doing the average force. Pretty much the same thing as last. All right, we're actually going to play the arrow game. Isn't that exciting? The rules for the arrow game is that if the variables are on opposite sides, you're going to do the same arrow. And if they're on the same side, you're going to do opposite. Okay, you think you remember that?
No, we've never learned this.
We're going to do it. Okay.
You will.
So it's the rules for the game. These are just the rules. Opposite is the same as opposite, right? All right. This is going to help you figure out like those test questions when they're like, if x increases, what's going to happen to the variable z squared?
How do we score? Where's the penalty box?
This isn't sports ball. Okay, so we're going to find out how force, time, and mass and velocity are affected in a collision. So the first thing we're going to look at is write down the equation. That would be easy. So the equation for this is impulse is equal to force times time, which is equal to the change in momentum, which is mv final minus mv initial. So how does the mass of an object affect the force of a collision? We're going to look at mass and force. So that's the only parts of the equation we really care about. So Ft, and I'm just going to, this is also basically m delta v. It just makes it a little bit easier. So I'm going to use that instead of spacing out my velocities. So if this is m delta v, how does the mass of an object affect the force of a collision? In this case, we're not looking at time or velocity. Those things you can say are constant. And if mass increases, what happens to force?
It increases.
It increases because they're on opposite sides of the equal sign. So they have the same arrow.
Oh.
So that means that they are directly related.
I see.
Good?
And but if they are on the same side, if
And
say
they are opposite or inversely related. Good? Okay, so how is velocity in this case? How does velocity affect force?
More velocity, more problems.
More velocity,
More force.
more force. So this one is also directly related.
but
Now, how about time?
the more time, the less force.
Good. The more time, the less force, because now they're on the same side, so they're going to have opposite. This means that it's indirectly related.
That makes sense.
Good. So you can use that in your standardized testing. I don't see any red cups. Is that accurate?
Oh, you see one.
I see one red. Okay, one was on. So now let's talk about it in a collision. In this case, a car crash. The most important factor in a car crash is the time that it takes for the person to come to rest. So if you think about it that way, you're going 40 miles per hour in your car, and you're going to get in a car crash and come to zero. So the impulse, the change in momentum, where's my pen? Let's look at this. Ft, impulse, delta p, mv final minus mv initial is also equal to m delta v. How's that? Oh, that's so any of those things we can look at. Let's look at ft and mv final minus mv initial. This is the one you usually use. I mean, I'm just picking out the pieces that I want to work with. I don't care about the rest of it. So we're going to kind of look at the force. How can we decrease the hurtful part, the force of it? So if this is a max velocity and your mass doesn't change in the car crash, and you're going to end up at 0,
And you start at 40.
and you start at like 40, so this is like 40 something, 40 miles per hour, or meters per second, whatever you want to do. Either way, you're going to die. And your mass is constant. Let's say your mass plus you in the car is, I don't know, 2,500 kilograms. I don't know what it actually is. It's just a big number that sounded scary. And we have force times time. So no matter what you do, you're going 40 miles per hour, you get in a car crash, and you're going 0. So this stuff is constant.
And force is going to be constant too, because it's mass times acceleration.
It's force times time. Now, how can we change this so that it doesn't hurt as much?
You say that force is constant?
Well, no, force isn't going to be constant. How do we decrease the death rate? We increase the time. In other words, we put as much soft stuff we can between us and everything else. This increases the time. Instead of landing abruptly, for instance, imagine jumping off a chair and not bending your knees.
Oh.
Yeah. Now imagine bending your knees. The only thing you've changed is the time of the impact. Your knees absorb that, and that creates a longer amount of time, decreasing the amount of force. So if you do this in a car crash, we can do it with seat belts, which just increases the time, and airbags, which also increases the time. Yes?
There's this whole thing that kind of just semi-related that just popped into my head. Nobody has ever died from falling. It's always the sudden stop that kills them.
Yep, that's exactly right. If you can decrease the sudden part of it, then you'll have a chance of living. That's what swimming pools, trampolines, parachutes, giant soft blob pillow things.
Meat shields?
Marshmallow seeds.
What?
Human meat shields?
Meat shields? I don't think that those are very soft. All right. So, if you can increase the time, you can decrease the force. Now, when is a time when you actually want to increase the force and decrease the time? Can you think of an example of that?
Baseball.
A baseball? Why?
Because you want to increase the force so that the ball goes farther, has a greater chance of getting a home run, and you and all your buddies can run home.
In a less amount of time. Is probably the biggest.
Because if you like hold it and it's like still maybe like super the bat and ball still on the bat somehow.
Yeah, they put like.
I feel like you want to increase the force and increase the time in order for that to work because you get the highest possible. That's why follow through is so important. Right?
You're in a fist fight and you throw a punch at the dude. You're going to want the most force but the least time.
There you go. Getting smacked in the face. Getting smacked in the face. That's excellent. Another one that I came across today, because I was doing momentum for another class, is a karate chop. The ones that could break all those bricks are the ones that could snap their hand back. Because they're going, instead of it just hitting it and going to 0, it comes back up. So you actually have a higher change in momentum. So it's decreasing the time because it's a snap instead of a chop, right? And that increases the force. So that was another one that I thought of.
I know it's like when people teach you to punch, they're like, when you hit, don't just keep it there, like pull it back.
Pull it back. Yeah, snap it. And that decreases the time and increases the force. Yep. Okay. Here is...
Decrease the time and increase the force?
That's only if the velocity is constant, right? If you went from some velocity to 0. What we're saying is you're going from some velocity and then pulling it back to a different velocity. So you're actually increasing the momentum altogether. Good? Okay. I have some clicker questions for you. Mike, do you have that red cup out for a reason? Okay. There we go. Question 1. If the momentum of an object is tripled, what happens to its kinetic energy? And give me 1 second to start this.
Well, wait, if you increase the momentum by increasing the mass, that changes things, right?
If the momentum of an object is tripled, what's going to happen to the kinetic energy?
Okay,
You
yeah,
have an
but,
equation just for this.
Yeah, the equation's up there.
okay, yeah, but the thing is that if the
I like the crappy ones.
okay.
Right? Yeah.
No, wait, no. I don't like it because it'll sometimes like double click letters and I'm just like, ooh.
Still waiting on 3 people. I think it's 3, 4, and 14. Actually, in this case, we're going to turn the recorder off.
No more recording.